Divya Prakash, I see you are there. Am I audible? Please write a message. Okay, and my slide is visible. Lecture 06 PDF file. Okay, good. Thanks. All right, it's time. I see very few students so far. I don't know the reason, but I will continue. I'll start the lecture because it's time. Anyway, it is going to be recorded and uploaded. So I hope all students will be able to see this part as well. Okay. So last lecture, we saw that there are two descriptions possible for mechanics of fluids. One is molecular, the other is continuum. I presented some arguments uh, based on which I concluded molecular description is not only very demanding resource-wise, it's also not necessary for most of our engineering applications. And for those engineering applications, continuum description is good enough, right? And continuum description is good enough for flow of liquids, mechanics of liquids, and also for atmospheric air. So flow of air past bodies, it is good enough for if we are near the surface, or even if up to a considerable extent, like aircrafts when they fly, these commercial aircrafts, they fly at about 10-kilometer altitude. Even their continuum is applicable. So as I pointed out last time, only when your spacecraft or aircraft is re-entering the atmosphere in those outer layers where the density is not adequate, their continuum description will break down. But for most engineering applications in which we have airflow close to the surface of the earth, it is still valid. Certainly for civil engineers, definitely no problem. Flow of air past a building, you can easily use continuum description. Don't have to think twice about it. So for the rest of the course, continuum description we will focus on. We will get into details of that. And I pointed out in the last lecture that with continuum, there are two possible ways to cast our dependent and independent variable set. First is what we call the Lagrangian description, and the other is Eulerian description. So we will see more details about these two possible ways of describing mechanics of fluids. You may recall I said for continuum description, the smallest entity is fluid particle, and that is considered to be point mass, a point mass in continuum description. I will refer to this phrase many times, and in my notes, many places you will see the acronym FP. FP means a fluid particle. For again some review we have seen in APL 100 engineering mechanics. We had this clarity that whenever you observe fluid motion, whenever you observe motion of a particle or a body, you need to have a reference frame in context. So motion is observed in contrast to or with in having a reference frame in the background, and that's what I'm denoting here. This is my way of denoting a reference frame. I put a cartoon here of a man, a person who is observing the motion. So he's tied to the frame and he's observing the motion of particle or body. So we will, whenever I talk about kinematics or dynamics in this course, there is a frame in the background, and here we will have fluid particles, the same smallest entity of in continuum description. And I will use this symbol RPO. What does RPO represent? RPO represents position vector of fluid particle P, right now what I've shown here, measured from location O, where O is fixed in frame F. All right, so this will be the order. P comes first, O comes second. P is the point, so the arrow, the position vector is going from O to P. I write P first and O second. Dumit's notation, what you must have referred to in APL 100. So now onwards, whenever I say velocity of a fluid particle or acceleration of a fluid particle, I may not specifically say that that is with respect to frame F, but that is implicit now. Whenever I talk about velocity and acceleration, there is a frame in the background, and motion is being observed in contrast to that. All right. Another item I want to review before I go to Lagrangian and Eulerian, and that is Taylor series. My assumption is you must have dealt with this in more detail in one of the recent courses you must have taken in the recent maths courses first year. I just want to review it because we are going to use it very readily in this course, very frequently. So if I have a dependent variable phi, and that dependent variable depends on one independent variable y, okay, so we can say phi is a function of y. Then I can write this series, which I have shown here on the right hand side. This is called Taylor series, and it starts with phi at y, and then it has derivatives, higher and higher order derivatives. Of course, we are assuming here phi is differentiable in finite number of times. Then only you can write this series on the right hand side. I have written here higher order terms, or acronym we put HOT, or HOT. Higher order terms means there are terms coming here with exponent of delta y being higher and higher, 4, 5, 6, 7, 8, so on. The use of Taylor series in our context would be that we will assume that we know the value of phi at a given location, that is, say y. At y, we know value of phi. And we also know the derivatives of phi, all derivatives of phi at that location. Okay. Armed with this much information, we can write the value of phi in the neighborhood of y. By neighborhood, I mean at y plus delta y. So y is my base value, and y plus delta y is the neighbor. Y is the base location, y plus delta y is the neighborhood location. So the value of phi at neighborhood location can be written like this. Further, we will assume delta y is very small. So once you assume that delta y is very small, it is reasonable to expect that the higher order terms, which have higher exponents of delta y, will become increasingly, or they will become less and less important. They will become less and less important, and thus the value of phi in the neighborhood of y can be approximated, for example, like this, where I have neglected all terms having exponent of delta y more than or equal to 2. Okay, this is one way to approximate the value of phi in the neighborhood of y. This approximation, which you are seeing in green box, this can be called a first order Taylor series approximation of value of phi at y plus delta y. Why do we call it first order approximation? Because the highest exponent of delta y in this is 1. So that's why it is we call it first order approximation. You can include the next term also, delta y squared term, then we can call it a second order approximation. That's going to be more accurate than first order, but we will see that for most of our needs in this course, first order approximation will be adequate. I can think of only one instance, which will come like 2 weeks later, where to get some physical insight about a term, we will need a second order approximation. But otherwise, this first order approximation is good enough for us. Okay, so this expression is applicable when phi depends only on one independent variable, that is y, right? So it is a univariate variable. Phi is a univariate variable. Now you can have a function phi which depends on many independent variables, and that is immediately relevant for us because we may have say temperature or pressure, which is like phi here, and it may depend on all three spatial locations and time, right? So I have one dependent variable, but four independent variable. So in that case, still I would like to make a first order approximation of phi in the neighborhood of x1, x2, x3, and t. And when I say neighborhood, what it becomes, so I want the value of phi at x1 plus delta x1, x2 plus delta x2, x3 plus delta x3, and t plus delta t. So that is the neighborhood, in the neighborhood of base location x1, x2, x3, t. So again, if I go for first order approximation, first order Taylor series approximation of phi in the neighborhood of the base location, this is what the expression will be, what you see here. Okay, so you see one term is del phi del x1, that comes with delta x1. Another is del phi del x2, partial derivative, that comes with delta x2. Similarly, partial derivative with x3 comes with delta x3, and partial derivative with time comes with delta t. And keep in mind, all these derivatives are at the base location. That's how Taylor series, that is what Taylor series tells us, that all these derivatives are computed at the base value. Base location, I shouldn't say base value, at base location. Okay, again, terms having higher orders have been neglected, and first order I'm saying because all these delta quantities x1, x2, x3, and delta t, they are having the maximum, the highest exponent that we have in our truncated series or approximate expression. The highest exponent is 1. That's why it is a first order approximation of this function. All right. So with this in our mind, this background, now I go and start describing what is Lagrangian description. What is Lagrangian description? First, I take up that. As I pointed out in the last lecture, the essential difference between the Eulerian and the Lagrangian description is in what we choose as independent variable to describe the flow field. Okay, flow field means motion of fluid in the domain of your interest. So in Lagrangian description, first independent variable is of course time. We will see in Eulerian also, time is still an independent variable. But the second independent variable in Lagrangian description is name of the fluid particle, identity of the fluid particle. So you may recall what I said in the last lecture. In mechanics, if you have a system of 100 particles, we can number them and give them an identity, or we can call them by some fancy names, John, Peter, like that. But the point is that we have to have the identity of fluid particle, or identity of the particle as an independent variable. So in this case, for a flow field, how do we name fluid particles? How do we give identity to fluid particles? So this is a very interesting way of giving identity to a fluid particle. It is Name of the fluid particle is given as the position vector it had at t equals 0. So you are interested in the motion of these fluid particles at t greater than 0 at all time instants, but you are identifying a fluid particle by its location, by the location it had when the motion started, right? So when the motion started, at the instant motion started, you know the location of all fluid particles and you name them like that. So I'm showing a diagram here. I hope it makes more sense. You see, this is the observer. He is interested in this particle, okay? And this is time t. So the particle he is interested in is here at time t. So what is the name of this particle? So name of this particle will be, or the identity will be, or it will be identified using what was its location at t equals 0. Same fluid particle where it was. Might have been here at t0. So at that instant, what was its position vector? That identifies a particle. It is like saying, it's like saying you go to a Connaught Place and you are looking for a person who 10 years ago was living in Bombay. So in Connaught Place, if at any instant there will be people from many parts of India, many cities in India. So how do I name them? So I name them. I am interested in that guy who 10 years ago was in Mumbai. And then you can say, now I'm interested in that guy who 10 years ago was in Ranchi or in Bhopal. Okay, so where they were at t equals 0, that gives them the name and you put that name on their forehead. Put that tag on their forehead. This is how we are identifying fluid particles. Okay, so in that way, t is already an independent variable. The other independent variable becomes y. All right, and then you will realize that in this description, when y is an independent variable, the current location of the fluid particle at this instant, that actually becomes a dependent variable, and that is denoted by what I have written here. So x plus t comma y, I have written the full sentence here. Current, that is at time t, that is what you see time t. Current location of that fluid particle, which was at y at t equals 0. Okay, so see, we are casting this already as a function, like phi as a function of y I was writing when I was talking about Taylor series. Similarly, we have a function here in Lagrangian description. So x plus is a dependent variable, depends on what? Depends on t and y. Y is a vector. Y is the vector, the position vector of the fluid particle at t0. Okay, so also I want to highlight that once you have in Lagrangian description, all dependent variables are given this superscript plus to make it very clear to the reader that we are talking about Lagrangian description. You will see in Eulerian we will not put any plus. So that is a cue to the reader that plus means we are talking about Lagrangian description. All right. So x plus is, or the current position vector of the fluid particle is a dependent variable. I hope you see this sense in it, because I'm not choosing that as independently. I'm choosing y as independently. Okay, identity. It's like the same thing. If I go to the example of Connaught Place scenario, I am asking where exactly in the Connaught Place area, where exactly is that guy who 10 years ago was in Mumbai? Okay, so identity is independent, time is independent because I'm asking at this instant, but I'm asking about what? I am asking about where is he exactly in Connaught Place. That is the current position vector, and that I hope it makes sense to you that this is a dependent variable. You will have to compute that. You have not chosen that value. Where exactly in Connaught Place? That is a dependent variable. Or I can even make it more general. Where is that guy who 10 years ago was in Mumbai? Where is he now? So that position vector is dependent variable. Okay. What are other dependent variables in Lagrangian description? They will be velocity, temperature, pressure, and density. Okay, and they will all come with velocities of a vector. So I will put an underbar, and it will come with a plus superscript because I want to convey to the reader its Lagrangian description. Similarly, P will have plus pressure, rho will have plus density, pressure will have all these will have plus to denote it as Lagrangian. Now let me make sentences here, full sentences, so that you grasp the idea very clearly. So if you see V underbar vector plus T comma Y, you know it is Lagrangian, and then if I ask you to make a sentence out of it, you will say current velocity because V current because it's time T, current velocity of that fluid particle. Now remember, velocity will always be associated with the fluid particle. Similarly, pressure, temperature, density. So you have to bring in a fluid particle, but which fluid particle? Which was at Y, what is coming here at T equals 0. Similarly, P plus Ty will mean current pressure associated with that fluid particle, which was at Y at T equals 0. And similarly, rho and temperature. All right. So independent variable, this is kind of summary, Lagrangian description, independent variable T and Y, the initial location of a fluid particle or the name of the fluid particle, and dependent variables are current position vector, dependent variable, velocity of that fluid particle, current location of the fluid particle, velocity of the fluid particle, and pressure, density, and temperature. Okay. So that is Lagrangian description. Now let's see Eulerian description. I hope when I talk about Eulerian, that you will even appreciate Lagrangian description even more strongly. That's what my hope is when you contrast it with what I'm going to do now. Now Eulerian description. Okay, same flow field. Flow field has not changed. It is the same what was being pursued in Lagrangian description. Same reference frame. So Lagrangian and Eulerian are not reference frames. They are description. The reference frame is the same, observer is the same flow field. It's just that we will choose independent variables differently. So what are independent variables in Eulerian description? They are time and location. Location of what? Right now, location of nothing, just a location. So there is a flow domain and the user has the freedom to put his finger on any spatial location. That is X. And since he has the freedom to put his finger on any location, X vector, X is the position vector, where his finger is right now, that is an independent variable. Of course, it is a vector independent variable. Same was with Y. I hope that is not confusing you. Y earlier and X, Y underbar and X underbar are, when I say a variable, I mean they are, it's a vector, it's a vector independent variable. Of course, inside it will have three components. So in scalar terms, X underbar has three independent variables and Y underbar had three independent variables. But when it is vector, I will still use a variable with the understanding you are seeing that it is a vector. That's why I use the word okay. All right. So here I'm not making any fuss about which fluid particle. I'm just putting my finger on a location. So what are the dependent variables? Dependent variables will be velocity and pressure and temperature and density. And the expression will be something like this. So V velocity is now a function of X comma T, right? X and T are independent variables. And what will be the meaning? The sentence that you will make will somewhat change. Vxt, when in Eulerian description, and you see there is no plus here. So no plus, you try to convey to the reader it is Eulerian description. So Vx comma T means current velocity. Okay, current velocity because there is T here. Now velocity has to be with the fluid particle. So which fluid particle? So you are not identifying any fluid particle. There is nothing favorite. There is no favorite fluid particle on your part. But velocity has to be associated with the fluid particle. What is that fluid particle? Current velocity of that fluid particle, which is currently occupying the location X. Which one is that? John Peter, I don't know. I don't know which fluid particle is that. That's not my independent variable. But whichever fluid particle is at X, I am talking about that. So that is Vxt. Similarly, Pxt will be current pressure associated with that fluid particle, which is currently at location X, and similarly rho and T. So the variable set will be X comma T, independent variables, dependent variables, velocity at xt, density, temperature, and pressure at x comma t. Hope it makes sense. Let me go back and see if I have any questions. So far, no questions. Okay. All right. We just summarized Lagrangian and Eulerian. Now, so there are two visual cues to see whether your description, when you look at this set or you look at this set, there are two visual cues we are putting for reader to make out to understand whether it is Eulerian or Lagrangian. First is, of course, the plus sign that I said. And also you see that in Lagrangian description, we put T first and then the initial location vector later. It's T comma Y, whereas in Eulerian we put X comma T. Again, there is no fundamental theory about it. It is by convention. So by convention, we have agreed that let's put these two cues. Eulerian first put a special variable and then time, and Lagrangian the other way. Further, to just make sure it is communicated clearly, also put a plus sign. All right. Okay, so now we have identified the set. Now let me ask some more questions related to, let's ask more involved questions pertaining to these descriptions and see how these descriptions answer those questions. So the first question I'm asking, and again, I am asking these questions because such quantities we will be dealing with when we start working on the equations. Now let us write the mathematical expression for, so this is the sentence I am putting. The current means at time t, the rate of change in temperature following that fluid particle, which was at y at t equals 0. Okay, so this is a relevant question that can be asked in Lagrangian description. So see, Lagrangian description has independent variable y and t, right? So that's what is being respected here. The person who is asking question is saying rate of change of temperature following that fluid particle which was at y at t0. So he has chosen y as independent variable. What will be the expression? So this will be the expression. I've written it here. T plus at t plus delta t comma y minus t plus at t comma y divided by delta t, take that limit, that should be the rate of change of temperature or rate of change in temperature when you follow that fluid particle which was at y at t equals 0, right? So that fluid particle, every fluid particle is moving in general, okay? And to make to find rate of change of anything associated with that fluid particle, mind you, you have to take two measurements, right? You have to take two measurements. Then only you will take the difference, divide by delta t, and then take the limit. Then only you will get rate of change. So two measurements have to be made whenever rate of change is to be computed. Now these two measurements are being made like this here, keeping y the same. Why y is being same? Because the user asked temperature following that fluid particle which was at y. So he's interested in that fluid particle. So that's why I keep y the same. Same fluid particle, two measurements made, one at T, another at T plus delta T, divide by delta T. This is what should be the rate, right? Physically, this is what it means. And then immediately you will recognize that in the language of partial derivatives, this quantity is precisely the partial derivative of T plus with time, right? Last class and even in last tutorial, I reminded you that whenever we put partial derivatives, it means that only this derivative is allowed to change. Every other derivative, only this variable is allowed to change, while all other variables are kept constant. That is the meaning of partial derivative. That's precisely happening here. We don't need to change y because it's the same fluid particle. Time is changing only, and that's why this expression in the language of mathematics or calculus is precisely partial derivative of t plus with time, right? Another question, what is the expression for acceleration of that fluid particle which was at y at t equals 0? Okay, and when I say expression for acceleration, it is implicit current acceleration at time t I'm talking about. So I want the current acceleration of that fp which was at y. What will be the expression? We know that, okay, pay attention to what I have in green color here. Note that to get acceleration of a fp fluid particle, we must make two observations of the velocity on the same fluid particle. Okay, wherever that particle goes, you have to make measurements of velocity on the same fluid particle and then take this kind of difference and divide by delta t. To find acceleration of a fluid particle, you cannot make first measurement on first fluid particle and make second measurement on second fluid particle. If you take the difference of those two velocities and divide by delta t, that is not acceleration. That is acceleration of neither the first nor the second. That is irrelevant quantity. So for acceleration, you need to keep the fluid particle the same, and that is what I am doing here. You see this expression. This must be the acceleration of that fp which was at y at t0. See, y I have kept constant, allowed t to go from t, allowed time to take an increment delta t, and you take the limit. This is what should be the acceleration. And then again, definition of partial derivative, you recognize you are taking derivative rate of change and you're not changing y, you are only changing time. So this must be partial of v plus t comma y with time. Okay. So if I give you v plus t comma y as a function of t and y, you will see this, you will see examples in tutorial set 2. I will give you some function, a times t plus b times y. Take this as the velocity field. And then I ask you find the acceleration of that fluid particle which was at y. What do? You just take that expression, take the partial derivative of its time, and set the y value whatever I am asking for, and that will give you acceleration of that fluid particle which I am interested in. Okay, so mathematically finding acceleration or rate of change of a quantity following a fluid particle, following that fluid particle which is at y in Lagrangian system, Lagrangian description, is very simple. Just take partial with time of the expression given to you. All right. Moving on. I ask a similar question, not the same question, but a similar question I can ask in Eulerian description. What is the expression for the rate of change in temperature associated with that fluid particle which is currently at x? So mind you, in Eulerian, you can do only this much. You cannot identify a fluid particle because it is not an independent variable. What is independent is x. So you can ask, whichever fluid particle is at x. I put my finger at a in the flow domain, and I say, wherever my finger is, give me the rate of change of temperature if I now start following that fluid particle, which is currently at x. Okay, I hope you are getting this idea. So I put my finger at a location, there is a fluid particle, and then I say, now you follow this fluid particle and tell me what is the rate of change in temperature of this fluid particle. Okay, that is a similar question that can be asked. Is this going to be partial with time of txt? And then mind you, since it is Eulerian, this function t, it does not have any plus, and it has independent variables as x and t. Okay, so remembering what we saw on the last slide for Lagrangian description, can we just go ahead and hurry and say that if I take the partial derivative at time of this, it will give me what I have written in the sentence form on the top? The answer is no, and I'll show you why it is no. We have to work harder to get this rate of change in Eulerian. Okay. So in Eulerian description, the answer is wrong, as I said, this partial with time. And I want to tell you what it actually means, and the partial with time. And my hope is when I tell you what it actually means in Eulerian, then we will be able to go to the right answer. So, and understanding why my answer is wrong will help me find the right answer in Eulerian description. So recall, the definition of partial derivative tells me this much, what I have written here. And what is this much? If it is partial with t, you keep x the same. Mathematically, you vary t from t to t plus delta t. Here, two observations have indeed been made, but the observations have been made at the same location x, right? When you are talking about del t, partial t with time. Two observations have indeed been made, but in those two observations, x remains the same. But then think about this, visualize the flow field. The fluid particle which is at x at time t, is it going to remain at the same location at t plus delta t? No, it will not be, because it is a flow, right? Every fluid particle is moving. So at the fluid particle which is at x at t moves to another location at t plus delta t. That fp's new location will be actually denoted by x prime, where x prime is the original location at time t plus velocity at the original location at time t multiplied by delta t, right? So I have shown a rough sketch also here to make you understand. This black location is a fluid particle is here at time t. And this is what you chose x as independent variable. So let's call this particle which was at x at time t as alpha. Let's call it alpha. So you made first measurements on alpha. I hope you see my cursor. You made the first measurement on alpha. So this is temperature of alpha, no doubt about it. But by the time you were ready to make the second measurement at the same location, alpha has moved on. Alpha has moved to new location x prime, which is actually differing from x by v xt delta t. Whatever was the velocity here multiplied by delta t time, it has gone there. And as alpha has left that space and moved on, another particle has used this opportunity and come and occupied this location at t plus delta t. Let me call it beta. So alpha moves on and beta comes at this location. So the second measurement that you are making at t plus delta t at same x, it is actually not temperature of alpha, it is temperature of beta, right? I hope you follow this, which means that in Eulerian description, if you just take a partial with time, then what you are doing is a funny quantity. I call it funny because see what is there. On the numerator, you have temperature of beta particle at t plus delta t minus temperature of alpha particle at t divided by delta t limiting value limit delta t going to 0. And I hope you will agree with me that this is not rate of change of temperature of alpha. It's neither rate of change of temperature of alpha, nor it is the rate of change of temperature of beta. It is rate of change of no fluid particle per se. All right, but you can call this local rate of change. What I mean by local rate of change? If you have a temperature probe which is fixed at x at all times, okay? If you have a temperature probe fixed at x at all times, then The rate of change that probe will measure, that is precisely what is partial of t with time. So it is not associated with any fluid particle. Partial with time is associated with only a probe that is fixed at that point. So this does not answer the question that I asked. However, it has some other meaning, which is different. Okay, so now that we have this understanding, let's try to precisely find this quantity. What is the expression for the rate of change in temperature associated with that fluid particle which is currently at x? So it means we will have to make the second measurements going to the location where the particle will be moving to at t plus delta t. So this is clear. We will have to make first measurement at x. The second measurement has to be made at x prime. You have to, whatever your probe is, you should be ready to move it to new location. Then only we will get the right data. Okay. So green dots are locations of the same fluid particle at two time instants now. So I am correcting my course of action. I am now following the fluid particle. Green dots are locations of the same fluid particle at two instants. What same? The fluid particle which was originally at x at time t. And then the same fluid particle is at x prime at t plus delta t. And these two vectors differ by v at x comma t delta t. All right. So rate of change of temperature, the same question. Now you look at this expression and I hope it will make sense that this is what we were actually originally looking for. You see the arguments of t here. So it is a limiting value delta t going to 0. There is delta t in the denominator. The first measurement is still t at xt, but the second measurement, you have changed the time and you have also changed the location. You have taken it to be x prime. Okay, to make sure you are focusing on the same fluid particle. All right. And then, as I said, that these two differ, these two vectors, x prime and x, they differ by this v at xt multiplied by delta t, velocity times time, that is displacement vector. So I can replace this x prime here in the first measurement by x plus v delta t. And this is what the expression will look like. And this is clearly not partial with time, what I have written. It is something else. What it is, we will see in a little while. What is the compact expression for this term? In Lagrangian, we focus on a particular fluid particle and we focus on. Okay, so Aditya, I will rephrase your question a little bit. In Lagrangian, in Eulerian also, you can talk about a fluid particle, but the identity of that fluid particle will start with a location. Okay, so I will say, what is the rate of change of temperature of a fluid particle that is at this location? So you are talking about a fluid particle, but its identity you don't know. You talk, you kind of make reference to it by its location, current location. Whereas for Lagrangian, you make a reference to a particle from its original location, and then you say what is the rate of change following that fluid particle which was at location y at t0. And here you will say, you can only say in Eulerian, what is the rate of change of that fluid particle whose exact identity I don't know, but happens to be at x location at time t. So what you are using word focus, I will say you, for more clarity and to make it less ambiguous, you write replace the word focus by independent variable. The question that you can ask in Eulerian is, you can ask only with reference to a location, and the questions that you ask in Lagrangian, you can ask with reference to the location of particle at t equals 0. All right. Okay, so this is the expression. I'm going to simplify it more. Let's see uh, uh, how we can simplify it, this expression. So now I commit myself to a coordinate system. So far I have talked only in terms of vectors, all x and v delta t, they're all vectors. Now I'm saying for simplification and a better understanding of what this is, let me choose a working coordinate system. That's what is the purpose of a working coordinate system. Purpose is to be able to manipulate tensors and simplify them. So now the time has come that I choose a coordinate system. And I choose my Cartesian coordinate system because it's the simplest and most of the times we use that. So I have this coordinate system OX1, E1, X2, E2, and X3, E3. And origin of the coordinate system I am keeping at the same point from where I was measuring position vectors without any loss in generality. So O can be any point. So as long as it is fixed in frame, we are fine. So O is my origin of the coordinate system as well. And then, then we see that you can write X and X bar in this manner, components. Okay, same coordinate system. Prime means, I mean, there is no change in coordinate system. Earlier, I used prime in a different context when I was talking about transformation rules. Don't confuse prime with that. Just two different vectors, prime and unprime. And let me represent Vxt delta t as this. So Vxt is a velocity, so it will have three components. So I'm writing that vector in terms of those three components. Okay. So since x prime is equal to x plus v times delta t, it means that in Cartesian coordinate system, first you can express each of these vectors in terms of e1, e2, e3. And then you can extract three scalar relationships. Three scalar equations are there, component-wise. So x1 prime and x2 prime and x3 prime, they are related to x1, x2, x3, and three components of velocity in this manner. All right. I go and plug it back here. I mean here, in this expression, I am putting this here. Actually, when I say I plug it back here, everything is happening within the arguments of t. T is a scalar, but only the arguments I will now start writing in terms of components of the vectors. So this is what it is. Txt can be written as t, x1, x2, x3, comma t, functions of four variables. And t at x plus v delta t, which is the new location at the new time instant. This can be written as x1 plus v1 delta t. So instead of x1, you have x1 plus v1 delta t. x2, instead of x2, you have x2 plus v2 delta t, and so on. And lastly, instead of t, you have t plus delta t. Right? Now I will invoke Taylor series approximation. Now, so what we are dealing with, I want to take x1, x2, x3, t as the base location for Taylor series approximation, and I want to find the value of temperature, the function, in the neighborhood of base location. So neighborhood is decided by what? Delta x1, which is v1 delta t, delta x2, which is v2 delta t, delta x3, which is v3 delta t, and delta t. So this is the neighborhood. And if you refer back to the that slide on which I showed Taylor series approximation, you refer back to that and you will see that this thing can be written approximately as what I have on the right hand side. So first term is the value of temperature at the base location, and then there are four derivatives appearing. The first derivative is partial with x1, the second with x2, the third with x3, finally it is with time. The derivative which is coming with which has partial with x1 must be having delta x1, but delta x1 in our case is nothing but v1 delta t. Similarly, delta x2 is v2 delta t. Similarly, delta x3 is v3 delta t, and delta t is delta t, like this. Right? So I have expanded it in this manner. And again, I want to remind you, I have not written it explicitly, but keep in mind all these derivatives are at what location? They are at the base location, x1, x2, x3t, by Taylor series formula or expression. Derivatives are at base location. All right, so we take this expanded form of the second measurement and put it back here. Okay, the expanded form or Taylor series approximation form for this, and this is anyway t x1, x2, x3t. And when you put that in the numerator, you will see that this base value will get cancelled out. The base value will get cancelled out because one is there originally, first measurement, and the second is coming from second measurement as its base value. Okay. So these two get cancelled out and you are left with four derivatives. One with time, one with x1, one with x2, and one with x3. And the ones that come with x1, x2, and x3, they have coefficients as the components of velocity vector at location x at time t. All right. So this represents this combination of four terms that represents rate of change in temperature following that fluid particle, which is at location x at this instant. So you put your finger in the domain. At this instant, you ask, what is the rate of change of fluid particle, which is right now at this location? Give me the expression for that. And that expression has four terms, four partial derivatives. And clearly you see it is not partial with time alone. Partial with time is a contributor, but that is not the full story. The full story comes from spatial derivatives. Okay. And now I want to take you back to like two lectures ago when we were defining different kinds of operations or operators for tensors. And I hope you will be able to recall what is happening here. You see, we have an operator acting on T, and that operator is what? V1 del x1, V2 del x2, V3 del x3. Go back and see that is precisely what I call the advection operator. The advection operator, V dot del. At that time, I said V is a vector. V could be any vector mathematically, but in fluid mechanics, the advection vector has V as velocity itself. So velocity dotted with a del operator that is coming here, which means that I can write this expression in a more compact coordinate system independent form, which I have shown here. This thing can be written, this whole thing can be written as partial with time. Time has nothing to do with coordinate system, so this remains. But the bunch of these three terms can be written as V dot del t. So not only it is compact, you will realize that once you come to a tensor form, that is now applicable for any coordinate system. So we made this derivation using Cartesian coordinate system. But once you have a derivation based on Cartesian coordinate system, you convert it into full tensor form. I mean, by full tensor form, I mean independent of coordinate system. So you have Cartesian coordinate system. From there, you go to you go to coordinate system independent form. And now this expression is available for any coordinate system, cylindrical, polar, path coordinate system, whatever you want. So this expression has that meaning, independent of coordinate system. All right, I will take one more minute and then I will wait for some question. There is a special symbol for this expression, this whole thing, what you see here. There is a special term, a special symbol for this. It's denoted by capital D dt in fluid mechanics. So capital D dt is a new operator, which is the sum total of partial with time and the advection operator. It is also called the material derivative or substantial derivative. It's called material derivative because you are following a piece of material while trying to find this rate of change. This piece of material is nothing but a fluid particle. Okay, it's not a derivative that you don't care of material, you fix your location and you find rate of change. That would have been this. But you have made special attempts to follow a fluid particle or follow a piece of matter, and that's why it is called material derivative. Thus, in Eulerian description, rate of change following the fluid particle which is at x at t equals t is this. Now, if I now extend this idea or ask you to extend this idea, what is the acceleration expression for acceleration of a fluid particle that is at x at time t? Okay. So if I want to find acceleration, we know rate of change, acceleration is rate of change of a fluid particle. You have to keep the fluid particle same. So implicitly, you have to follow the fluid particle, make two measurements of velocity following the same fluid particle. So that word follow comes. You will have to move with the fluid particle. You will have to direct your probe at the next time instant wherever the particle goes, and that is exactly what is represented by big D dt. So in Eulerian description, the acceleration of a fluid particle will be found like this: del t bxt. The entire vector becomes the operand, right? It is being operated by del t, and then for advection operator will also act on the entire velocity vector. So it's v dot del v partial with v, partial with time, add all these up, and that will give you acceleration of a fluid particle which is at x at time t. I stop here. I go to see if there are questions. Others who want to leave, maybe. This now applies to rate of change of any quantity, Amitesh, precisely. That is the idea. So partial with time plus advection vector v dot del, this operator, this can be used for any quantity. And you saw I just use it for velocity also. Velocity, pressure, whatever, I mean, doesn't matter. As long as you ask this question, what is the rate of this quantity, fill in the blanks, blank quantity, following the fluid particle which is at x at time t, this formula, this relationship will be applicable. So please read the lectures. I don't think everybody would have gotten the idea because there is some mathematics involved here. Variables are changing from one place to another. Read it carefully, and I'm sure once you read it, you will get the idea. So now no need to bother about x prime, right? Are we just exactly? That's a very good point, Satvik, what you have pointed out. Indeed, with this expression, that's a very good observation. You see that this v dot del t has doesn't need anything from t plus delta t or x prime. T is at xt, v is at xt, partial with time, this derivative is at xt, and v dot del, whatever spatial derivatives are involved, they are all at xt. So that is enough for you to predict the rate of change. Very good observation. Yes. Um, yeah, I'm still here. Any questions, please type. So students have been were asking questions about physical meaning and physical meaning of various tensors and all. And I kept telling you that let the context come and we will see. So this is an example, advection operator. If you would have asked me at that time without any reference to a particular vector or any context, I was reluctant. But now with velocity, now with v as velocity, you see a physical meaning. Physical meaning is that that is the contribution coming over and above the partial derivative term to give you the full rate of change. I mean, all these fluid particles which I have shown at different location, There is some physical insight represented by V dot del. It takes into account the fact that fluid particle doesn't remain at the same place. The change is coming due to its change in location during time t. During that time delta t is captured by V dot del operator. Sir, will you explain once again what Aditya has asked? Okay, so Aditya is asking, Lagrangian, we focus on a particular fluid particle, while in Eulerian, we focus on a particular position. So all I am suggesting to Aditya is that don't use the word focus in this way. You can say that in Lagrangian, we can probe a fluid particle, okay, or we can talk about a fluid particle in Lagrangian with reference to its initial location. That will be an independent variable. You will pick up a fluid particle based on its initial location. In Eulerian, you do not have that freedom to pick up a fluid particle and talk about it from its initial location. For Eulerian, you will have to pick up a fluid particle only by putting your finger on the domain. I mean, using X as independent variable. That's what I tried to convey to him. You pick up a fluid particle based on X in Eulerian and it's by its initial location and with its initial location in Lagrangian. We can, in both the description, we can talk about